This is a short video about the beginning of section 1.2 in Stein's elementary number theory book. So the overview of section 1.2 is concerned with the following questions. Number one, are there infinitely many primes? Given any two integers a and b, are there infinitely primes that have kind of this linear form, ax plus b, where x is some other natural number? And finally, how many primes spaced along, or how are the primes spaced along the number line? In other words, is there any pattern that governs how the primes, pop up as you go farther on the number line? So we'll look at the first one here. I'll skip this. This sort of tells you the answers to that question. But I'll skip to the first part, which is that there are infinitely many primes. And in fact, you see maybe the result right here. It's actually due to Euclid. Remember, Euclid lived around 300 BC. And it always blows my mind about just the type of mathematics that people were doing so long ago, like highly non-trivial things. But anyway, in the beginning here, what is this about? This is to sort of give us some insight into what might have been Euclid's idea for his proof that there are infinitely many primes. And so the thing that we're supposed to notice is when I say take some product of primes and add 1 to it, it looks like I get another prime number, 31. Or if I do 2 times 3 times 5 plus times 7 plus 1, I get another prime. Now, maybe you're thinking oh my goodness, is it true that P1 times P2 times Pn plus 1, is that always prime? Is that true? Is that some kind of crazy pattern? And the answer is no, because check out down here. If you take 2 times 3 times 5 times 7 times 11 times 13 plus 1, you get 30,031, which factors as 59 times 509. The point, though, is you'll see how we use sort of this idea in Euclid's proof. So let's jump into that then. So let's jump into Euclid's proof again that there are infinitely many prime numbers. So this is a proof by contradiction. So suppose to the contrary that P1, P2 through Pn, those are all the primes that we have, say. So let's say I've only got those n primes and that they're all, of course, distinct. So what we're going to do is the goal of this proof is to obtain a prime Pn plus 1 that is not in this list. And the way that we're going to do that is by defining the following natural number, which, sort of consistent with what's going on up here, I'm going to take the product of all the primes that supposedly exist, and I'm going to add 1 to it. Now, I'm not trying to say that capital N is necessarily prime here. I'm not making any such assumption, but this is just kind of what's consistent with going on up here. So let's see what's going on. So here's this number n. It should have a prime factorization. So notice too, this is not factored, right? We added 1 at the end. So n, though, from the fundamental theorem of arithmetic, we should have a prime factorization. It should look like some product of primes, say q1 through qm, where I know there's at least one prime, say, this has at least one prime in this product. That's how we mean m should be bigger than or equal to 1. Maybe n itself is prime. Now, let's compare this expression for n with this expression for n. So if q1, the first prime, if it's equal to one of the primes that I know about, let's think about what would happen then. So what should I do? Okay, let's say q1 is equal to pi for some I. Now read this. Well, that says that pi should divide n. So pi divides n. Keep that in mind, and we're just right here in the proof. But now think about, okay, pi divides this number n. Well, pi should divide this expression too. Well, now think about getting 1 by itself here. So I could factor a pi off of n, but I could also factor a pi off of this. So think about, you would have something like, n minus p1 blah 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 pn equals 1. You could factor pi off of both of these. So pi times some number is equal to 1. That says pi divides 1, which is ridiculous since pi was supposedly one of my prime numbers that I know about. So what does that mean then? So where are we at as far as this proof goes? Pi has to divide n minus 1, and so of course pi has to divide 1, and that's a contradiction. So that's where we're at so far. So what does that mean? Well, q1 can't be any of the pi's that I know about. In other words, in this prime factorization of n, none of these can be one of the q's. So what do we have then? We have a prime that's not in my list that I know about. So I've shown that that list grows. And the idea that there's infinitely many of these, right? I could repeat this argument. So there are infinitely many such prime numbers. And at the end, just try to make sure we're not getting the wrong idea here. We're not saying that when you take the product of primes and add 1 that it's prime, just to remind you of that. And the last thing in this little section here is just a funny joke, and it's due to this Dutch mathematician Hendrik Lenstra. Maybe I could say he's got a Wikipedia page. You could check it out if you want. He did some work in computational number theory. Let's see here. Well, what's his joke? That there are infinitely many composite numbers, and the proof of it is in order to get a new composite number, all I have to do is multiply the first n composite numbers to it, and then don't add 1.